And pen is acting up today. I find it works fine if I keep my sleeve like that, which is why I'm doing this. It looks strange. I don't know why. It has never behaved badly before, but check it out. If I want to talk about lim as x goes to infinity. See that? When I do this, it's perfect. Maybe the chemistry of my skin has changed today. We were talking about infinite limits. That is the limit as x goes to infinity of this or that. And we were talking specifically about how do you do this when you're looking at equations. If you're looking at a graph of something, this limit is just equal to wherever the curve goes when the x goes out forever to the right side or to the left side if it's going to negative infinity. But what if you are looking at an equation? There are some simple tricks that you can do to evaluate limits like this. Limit as x goes to infinity of something like that. All right, the simple trick, I think we did this one at the very end last time. The simple trick was to divide on the top and the bottom, divide everything out by x. What you get is x over x plus 4 over x over x minus 1 over x. And then you can simplify a little bit here. All of those x over x's become 1s. And then this other thing is just going to stay as a 4 over x. And then I got 1 minus 1 over x, right? And when I let x go to infinity here, that means the x is going to become very, very big. And everything you see with x in the denominator will turn into zeros. Because this is like 4 divided by something very, very big, which is basically 0. This is like 1 divided by something very, very big, which is basically 0. And so this becomes 1 plus 0 divided by 1 minus 0. Just each of those things with the x's in them turned into zeros. And then whatever's left over is what the answer is, which in this case is just 1 over 1, which is 1. So the limit of that guy is 1. All right? I want to do a few more like this. It turns out there are some patterns which can allow us to come up with a very, very nice trick that will let you answer questions like this immediately. So actually, there's a way to just look at this and instantly say the answer is 1 if you know the correct things to look for. So let's just try a couple more, and then I want to sort of step back and see if we can find any patterns in all of these. How about one? I'm going to use a different name for the variable. This is something they do in the homework all the time. Use h instead of x or whatever. All the same stuff, just calling it something else. How about 3h squared minus 7h plus 1 over 2h squared plus 4. All right. I'm going to try to do the same trick like I did before. So what I did before was dividing everything through by x. Remember, the point of that, the reason that worked is it makes all the x's go into little denominators. Now, here I'm going to do a similar thing with h, but actually, because I see h squareds here, I'm going to divide everything by h squared. This is because my goal is to move everything into denominators. And if I only divide by h, that's sort of not good enough to cancel the h squared. You need to divide. Actually, the trick is to divide by the highest power of the variable that you see. And I see h squared, so I'm going to divide everything out by h squared. So this becomes 3h squared over h squared minus 7h over h squared plus 1 over h squared divided by 2h squared over h squared plus 4 over h squared. Right? Simplifying what we can here, I'll go down here. 3h squared over h squared, that's just 3 minus, okay, this is 7h over h squared. What does that simplify to when I cancel as many h's as you can? It's like I got one h on top and 2 h's on the bottoms. H? Somewhere there's going to be a h.
Would it be 7 over h?
Yeah, so we're still going to have 7 on top, and the h that's left over will be on the bottom, because there used to be 2 on the bottom and 1 on the top. You cancel 1 each, I get 1 h on the bottom. I said 1 each, not h. but it is also 1h. All right, 1 over h squared is just going to stay like it is. You can't cancel any of that. And on the bottom, 2h squared over h squared becomes just 2. 4 over h squared, you can't cancel, is just 4 over h squared. All right? And now I'm going to do the limit as usual. All the stuff with h's on the bottoms becomes 0, and the other things just stay like they are. The 3 and the 2 will stay like they are, but everything else becomes 0 because all the other stuff has h's in the denominator. So this is 3 minus 0 plus 0 over 2 plus 0. The answer is 3/2. All right? This is how we do it. Yeah?
You might have explained this last class, but why does everything turn into a 0?
Yeah, it's because, so this is one of the sort of, I wrote this as kind of a formal rule, but it is a fact that the limit as x goes to infinity of 1 over x to the n equals 0. This is because you think of this as, this is like 1 divided by some number which is becoming very, very big. So it's like 1 over a million or 1 over a billion. That's basically 0. And when you do the limit, as x actually becomes infinite, this really equals 0. And that's what these things are. The 7 doesn't make any difference because you're dividing by an infinite thing. Yeah. Thank you for the question. All right. This one, anyway, was 3/2. Little spoiler alert. I told you we were going to have some pretty awesome tricks here. And I said, if you know what to look for, you can actually look at this and immediately say the answer is 3/2. Can anyone say, where did this 3 and the 2 come from in the original thing? Yeah.
The first, like, 2 numbers.
Yes. The little number in front of the other thing. Those are called the coefficients, right? This 3 and the 2, they are the coefficients on the h squareds. Everything else will become zeros. The only thing that survives is the coefficient in front of the highest power on h or x or whatever. All right, so this is a theme. What you see in the answer is basically just equal to whatever the coefficients were that you started with. Now I'm gonna say that in more formal language. You can see that actually happened in this example too. The answer was 1, which really came from 1 over 1. That's because these coefficients here and here are both 1. It's a little harder to see, but.
Is that the same for like almost all of them?
Yeah, this is basically always true, and I'm going to say specifically when this will always be true. But what this means is, in a problem like this, more or less you can say the answer faster than I can write the formula. If you know the appropriate thing to look for, there's basically no work at all to be done with these. But I'm going to say exactly what to look for in a moment. I just want to do a couple more examples because what I just said does not always work out. Although, in those cases, there's another simple principle to keep in mind and everything will work fine. How about this one? X squared plus 7 over x to the 5 plus 3x. So I'm going to try to do it the same way, and that is by dividing everything by the biggest power of x you can see. In this case, that would be x to the 5. So I'm going to divide through everything by x to the 5. We get x squared over x to the 5 plus x to the 7 over x to the 5. What? Sorry, 7, not x to the 7, just 7 over x to the 5, divided by x to the 5 over x to the 5 plus 3x over x to the 5. Simplify each of those guys. I hope you remember in one of these little fractions with powers of x's, basically what you want to do is subtract the exponents. You cancel them, leaving behind some on the top and the bottom, depending on which one was more. So x squared over x to the 5, there are extra ones on the bottom to the tune of 3 more, right? There's 2 x's on top and 5 x's on the bottom. You cancel 2 of them. What remains is 3 on the bottom and none on the top. Plus 7 over x to the 5 just stays like it is because there's no canceling x's. X to the 5 over x to the 5 is 1 plus 3x over x to the 5. What does that amount to when I cancel them? Somebody want to say it? 3x over x to the 4. Yeah, great. Okay, And now I'm going to do the limit by making things into zeros as appropriate. Anything which has x's on the bottom becomes zeros. So this is 0 plus 0 over 1 plus 0. That's 0 divided by 1. And what does that mean? That's just 0, right? That was kind of a trick question. Sometimes it's a DNE. If it's something divided by 0, that's a DNE. But if it's just 0, 0 divided by something else is still 0. So that's no problem. 0 on the top is not a problem. The answer is 0. All right. Now, in terms of the cute tricks, this may be a little different than what you expected because this 0 is not actually any coefficient over here. Why did we end up with a 0 here? Really, we ended up with a 0 here because there was a 0 on the top of the fraction. And that happened because everything on top became zeros. If you think about why did that happen, really it's because the power on the top, x squared, was less than the power on the bottom, which is x to the 5. And so that when we divided by x to the 5, it ended up making everything on top into 0. All right? This is what happens when the degree of the polynomial on the top is less than the degree on the bottom. The degree means the highest exponent that you see. If the degree on the top is less, you will always get 0 on the top, which will make the answer 0. Yeah?
So we can use the trick unless the degree is higher on the top. So like if it was like 2x to the 5th over 5x to the 7th, that would be
different. Yeah.
because
no, that would be 0.
Yeah,
because it was bigger on the bottom.
That's what I was asking.
Yeah.
If there's a coefficient that's like larger than 1, it makes no difference.
Doesn't matter.
Okay.
Yeah. In this case, had there been some coefficient here, it wouldn't matter because that part is turning into 0 anyway. Yeah, great. All right. So this is what happens if the degree on the bottom is bigger. You're going to end up with 0. We should also talk about what happens if the degree on the top is bigger, and then that I think will sort of do it in terms of all the different possible eventualities that could occur. So what about, I'm just going to make up one where the degree on the top is bigger. How about that? Here the degree on top is bigger. Let's see what happens if we try the same old business. I am again going to divide out by the biggest power of x, which in this case is x to the 4. So I will divide on the top and the bottom by x to the 4. I get 3x to the 4 over x to the 4 minus 1 over x to the 4. Divide by x cubed over x to the 4 minus 7x squared over x to the 4, like so. And do some simplifying if we can. 3x to the 4 over x to the 4 is just 3, minus 1 over x to the 4. I have to leave like it is. And on the bottom, x to the 3 over x to the 4, we cancel 3 of them and 1 remains, so this is 1 over x. Minus, here we can cancel 2 of them and get 7 over x squared. And then I do these limits. Those things become zeros. 3 minus 0 over 0 minus 0. This is 3 over 0. And what is your interpretation of that? This means that the limit does not exist. If you see 0 in the bottom and a non-zero on the top, this means that the limit does not exist. Any questions about that one? I hope that I did that one a little faster than the others, but this is very similar to the others. All right? I think at this point we can make some general statements about what's going to happen in terms of tricks here. It all has to do with the degrees on the top and the bottom. In this case, we can see if the top is smaller than the bottom, the answer is going to be 0. Here, if the top is bigger than the bottom, you can see the answer is going to be does not exist. And again, it doesn't matter what the constants are or anything, because you end up getting something over 0. All right? And if the degrees are equal on the top and the bottom, that's this scenario where you end up with this coefficients fraction. So I'm going to try and summarize this, and this is going to be kind of long-winded, but it's very, very easy to make use of. And I think if it's up to me, I would suggest that you memorize this as a trick because it makes these problems. You can always just say the answer immediately. Now, if you forget how to do this, you can go through all the steps and work it out. But I would suggest you just remember this theorem. Theorem is like a mathematical word for just sort of a true fact that we can prove mathematically. So it says if we have a rational function p of x over q of x. A rational function just means a quotient of polynomials, a fraction where the top and the bottom are each polynomials. All right, then, if the degree of p is bigger than the degree of q, that is, the degree on top is bigger than on the bottom, then the limit x goes to infinity of p of x over q of x does not exist. All right? If the degree on the top is bigger, the limit does not exist. If the degree on the bottom is bigger, the limit is 0. So if the degree of p is less than the degree of q, that means the degree on the bottom is bigger. Then the limit x goes to infinity equals 0. And if the two degrees are equal, here I have to say in words, although it's still a simple answer, then this limit is the ratio of the coefficients on the highest degree terms. We made it for the best part. Can I fit it all on the screen at the same time? All right. Then the limit is the ratio of the coefficients on the highest degree terms. This whole trick, provided that you can remember it, makes these kinds of questions very, very easy to answer. So I would suggest that you remember this, and then on the tests or on the homeworks or whatever, you can basically just immediately write the answer for any of these problems without doing any extra steps. I just want to do a few examples. Like I said before, you can basically say the answer faster than I can write the problem when you are answering questions like this. So how about the lim as x goes to infinity of 8x squared minus 3x plus 1 over 2x squared plus 4x minus 5? What do you say? You should look, first of all, identify the degrees on the top and the bottom. Are they equal, or which one is bigger? And then do the appropriate rule. So first of all, are they equal, or are the ones bigger or the other bigger? What do you say?
Yeah, they're equal.
They are equal. Yes, these are all very easy questions to answer. The degree is just the highest exponent that you see. In this case, they are both degree 2, so the degrees are equal, which means the answer is the ratio of the coefficients. That would be on top, the coefficient of the degree 2 is 8, and on the bottom it's a 2. So this is 8 over 2, which of course is 4, and that's the answer. There's not much more to it. All right. How about this? I could, these questions are basically always easy. I could try to couch them in language which makes it, slightly harder perhaps. How about find any horizontal asymptote for this function. Find any horizontal asymptote. Now, this sounds like a completely different question, but you will recall that a horizontal asymptote is the same thing as asking about what is the limit as x goes to infinity. It means where does the graph go when the x value gets super big. So this question, find a horizontal asymptote, that is just the same as if I were to ask you what is the lim as x goes to infinity of that same thing. And what do you say? 2 over 8, yeah. They are equal degree 3 on the top and the bottom. So you take the ratio of those two coefficients, which are the 2 on the top and the 8 on the bottom, which is 1/4. Although if you want to say 2 over 8, that's fine. All right, that's all there is to it. I got a few more. Can I just to make sure everybody knows the tricks? How about, I'm just going to write a bunch of them. This is the time when I would like walk around the room and see how everybody's doing. Although these ones are so easy, I think maybe we can just sort of shout out the answers once I write a bunch of them down. I may try to play some very simple tricks on you in the questions. So you want to look carefully, but really nothing can seriously change that makes these questions any harder. All right, can we just sort of go through these and say the answers? How about this one here? In all cases, you should be looking at the degrees and then do the appropriate thing based on the degrees. Someone want to shout it out? Someone I haven't heard from, perhaps? What do you think? 1/3, yeah. So here you don't see it, but the coefficient on top is a 1 right there, right? If there's no coefficient written, you read it as a 1. These are degree 2 on the top and the bottom, and so the answer is 1/3. Great. What about this one here? You will notice I'm being very slightly sneaky here, that I wrote the polynomials in a weird order. So you have to look at the degrees, which is the highest power that you see, which is not necessarily the first one that I wrote in the list. But anyway, what do you say for this one? Yeah, this is a DNE because the degree on top is bigger, right? The degree on top is 3. The degree on the bottom is 2. That means this is a DNE. That's because the degree on top is bigger. How about the next one?
0.
That's a 0 because the degree on the bottom is bigger. This one here, that's a 0 because the degree on the bottom is bigger. All right, how about this guy here? Yeah, this one you have to be very slightly careful to take this as your top term and this as your bottom term. They're out of order, which is fine. You also have to remember to use the minus sign as part of the coefficient. So this one, the answer is -7/2. All right. One thing that I would like to point out about this one is, I don't know if anybody noticed, right here, I put negative infinity rather than just infinity. All the other ones are infinity. This is something I meant to write. Would you mind if I go back up here and just add it into the rule here? I meant to squeeze this in. Sorry to do this. Same exact rules for x going to minus infinity. All right? If you see the negative infinity, it doesn't mean like you get the opposite rule or something like that. You don't have to make the answer negative or anything like that. The same exact thing. The reason it basically doesn't matter at all if the x is negative or positive infinity is because this is all based on the fact that 1 over x is becoming 0. And 1 divided by a huge positive number is close to 0, and also 1 divided by a huge negative number, that's also basically 0. So the whole thing works exactly the same. This right here, I'll just for emphasis, I will say that right there doesn't matter. The fact that it's negative infinity rather than positive doesn't make any difference. Okay, what about the last one there? This one here, I am kind of trying to be a little tricky with you. Anybody see the trick? Yeah, see that? I'm messing with you a little. X is going to 2 rather than infinity. Does that make any difference? The answer is yes, that makes a huge difference. In this case, x going to 2, you don't do anything like in that trick, right? This whole trick is only when x is going to infinity or negative infinity. So don't try and do it in other situations when x is going to 2. Sometimes people ask me, well, wouldn't it be easier if we did it with the trick? Well, yeah, it'd be easier, I suppose, but not correct. You can't do that this way. So don't do all of that stuff. You have to do this completely differently. This would be more like a question that's on our homework for tonight. They ask you all the time about find the limit as x goes to whatever. What should I do in order to solve this? Yeah, you try to plug the value in. This is the thing where you just plug it in. If you get 0 over 0, it means you have to go back and simplify, but I don't think that's going to happen in this case. I'm just going to plug it in. This becomes 2 times 2 plus 1 over 3 times 2 minus 1. That's 5 up top and 5 on the bottom. 1 is the answer, all right? By completely different methods. So this is just a little beware. Don't try this trick on everything. It's only when the x is going to infinity or minus infinity. Otherwise, you do it by plugging in. Can you plug in just with the infinity? The answer is not really. Infinity is not a number, so it doesn't really make sense to plug in the infinity. That's why we do it this other weird way. All right? Anybody got any thoughts about that? This is all I need to say, I think, about limits at infinity. All right? That's another thing on the checklist. In my opinion, this might be the easiest one of all of them. If you know the trick, you immediately can write the answer, and there's not much more. There's not really any way that it could be much more complicated than that. All right? Yes?
Do you ever like require us to show our work though, or like do you just straight up?
No, not on these ones.
Just
I would
okay.
expect you to just write the answer.
Okay.
That's it. Yeah. Yep. All right, great. Let's go on to the next thing then. The next thing is called continuity. Continuity. This is something that you've probably heard of before in high school or whatever. Continuity, I mean talking about whether a function is continuous or not. Some functions are continuous, some are not. That is, so the way that this is typically described, like in high school or even before, I don't know when people learn about continuous functions. This right here, this one is continuous. What that means, the way some people, sometimes describe it, this means that you can like draw the graph without picking up your pencil or something like that. It means the whole thing is like one nice, connected, continuous thing. That's what it means for the function to be continuous. That's not really a very good definition because I use the word nice and continuous, which are nice is not a very nice, not a very mathematical word, and you probably shouldn't use the word continuous in the definition. But one thing I want to talk about is what exactly is the proper thing to use for the definition. But anyway, that's an example of something that is continuous. Something that's not continuous would be one of these guys, if it has this kind of thing, right? That's not continuous. Not continuous because of that spot where it breaks in half, right? This is a curve which has a break in it. That means it is not continuous, and there's some sort of technical language that we use for that. Like for instance, if that was at x equals 3, we would say f of x has a discontinuity, or sometimes a discontinuity point at x equals 3. All right? That means at that particular x value is where the funny business happens, where the curve breaks apart into two pieces. And that's called a discontinuity point. All right? This is the basic idea. I think it's a very ordinary kind of idea that everybody can understand. But we should talk a little bit about technically what exactly is the proper definition. This is something that mathematicians like to get super specific about. What exactly is the definition of continuous, rather than just saying something wishy-washy like it makes a nice connected continuous line. Those are not technical terms that I'm using here. I'm going to say something a little more sophisticated than that. So what does it mean? Here's the real definition. This is going to be slightly, I guess, slightly technical, not so bad though. It says some function f of x is continuous at a point A. So this looks weird, but this is the way that our book defines it, and this is sort of how everybody talks about points. Unfortunately, they use the letter A. This is a variable, so this is some number here. Whereas this A that I wrote over there is like the word A. Sorry, that's confusing, but this is how everybody writes it. F of x is continuous at a point A, some number A, when three things have to be true in order to be continuous. The first thing is that f of A exists. So my sort of interpretation, I'm going to write the three things and then give a little commentary. What each one means. This means that the point actually exists. If you want your function to be continuous at a particular point, there has to actually be a point there. If that point is missing for some reason, then it's automatically not continuous. All right. So it's continuous when, first of all, that point actually exists. Second of all, this limit, lim x goes to a f of x, exists. All right. My interpretation of that is that, remember what the lim represents? It means that this is where the curve goes to. The y value along the curve actually exists. So my interpretation of that would be something like, the curve actually exists. Here. All right? So in order to be continuous, there has to be a point there, and also there actually has to be a curve there. Yeah?
When you mean the point actually exists, does that mean like the line goes through that point?
It means the line goes through that point and there's not like an empty circle there or something like that. Yeah. Well, actually, it doesn't exactly mean the line. So it's kind of like these two together mean the line goes through that point. Because this means there is a point. This means there is a line. And then the third thing I'm going to say is the point is actually on the line. So this is the third thing. Oops. The first thing means the point exists. The second thing means the curve exists. And the third thing is going to say where the point is the same as where the curve goes. And that is just f of a equals lim x goes to a f of x. Where the point goes is the same place as where the curve is going. Everything is where you want it to be. The point is actually on the line. It's not somewhere else. All right? So that's my interpretation of this. The point is on the curve. It actually sits on the curve rather than being displaced somewhere else. All right? So this is the technical way of saying exactly what you mean by I can draw the thing without lifting my pencil or something. That's kind of informal language. This is more formal way of saying the same thing. All right. So for example, I just want to look at what exactly here, if you're looking at a particular example, can you identify based on the three properties there, is it continuous or not? So something like this, which has maybe this kind of thing, where that's the value. Say this is 1 and this is 2. Here we have, I want to just check the three things. Is it true that f of 1 exists? Yes, because f of 1 equals 2, because the y value here is 2. Is it true that the limit exists? Lim x goes to 1, f of x. That means where does the curve go to? What's the y value along the curve near this point? And that would be also 2, right? So limit as x approaches 1 of f of x also equals 2. And these two things are equal. So it is continuous. Equal meaning they're 2 both times, right? The answer is the same. That means the point is here, also the curve goes through here, and they all meet up at the same place, which is y equals 2. So that one is continuous. Well, specifically, I should say, it is continuous at x equals 2, right? Because that was the specific point that I was talking about. Here, let's just try one where it's not continuous. Not continuous would mean something like, I mean, it could mean a lot of things, but how about this with the empty circle and the filled in circle thing? Let's say this is 3 and 1 like that. So here I could say, what is f of 3? Also, what is lim x goes to 3 f of x? And I want to say, what is f of 3 here? It is 0. The y value at x equal 3. I use the filled in dot. The y value is 0. So this is 0. What is the limit? I think it does exist. Yeah, I think it's 1. I heard somebody say 1, and some other people say some other things. You're all right if you're the person who said 1. The limit means where does the curve go, and that is the y value here. The curve is going through y equals 1. So this is 1. All right. Now here, each of those things exist, but they are not equal. They're different from one another. So these are not equal. So it is not continuous at x equals 3. All right. This is the somewhat technical definition of continuous. Any thoughts about that? Great. Now, these examples have been based on looking at the picture, but if you know me, you know I like to be able to do things without looking at the picture. Most of what we do in this class is based on looking at formulas for things and answering questions based on just looking at the equations, not looking at pictures. So let's try to do similar things. If I show you an equation, how about, here's an example to start us off. I can ask you, are there any discontinuity points? Or is it continuous everywhere? So one way to answer this question is to draw the graph on your calculator and just look at it and see if the curve looks continuous or if it has breaks in it. But I don't want to get into doing that because I want to be able to do this without looking at the graph. The question that should concern you, or what you need to worry about, is we need to worry about 0 in the denominator. Which causes an asymptote, right? This function here is all nice functions. These are polynomials, right? The top is a parabola, the bottom is a line. So there's no funny business about just like random points which are broken apart from the curve. But you should be concerned about 0 in the denominator, which causes an asymptote, because if there is an asymptote, then the curve might look something like this, and that's not continuous because of the asymptote, right? So when I ask you, are there any discontinuity points, you can detect this by figuring out, are there any points which make the denominator equal to 0? And in this example, there are. So here, we will get, for this particular example, oh, I picked up the line too. We'll get a discontinuity point when the denominator equals 0. Can anyone say, I mean, this one you can just sort of look and by common sense tell me, when is the denominator going to equal 0? For which x's? 2. Yeah, for x equals 2, that denominator will equal 0. This you can just sort of look and guess. If it were a little more complicated, as we're about to do some that are more complicated, you could set this up like a little equation and solve for x, right? You set the denominator equal to 0, and then solve for x. Here you would just add 2, you get x equals 2. So that is a point of discontinuity for this function, is at x equals 2. All right, this is really what you need to be wary of when I ask you about discontinuity points for functions, is look out for the denominator becoming 0. I have a more interesting example, and then I have one for you to try, and that might do us for today. So more complicated, slightly more complicated example here. How about find any points of discontinuity, and for each one, find the limit as x approaches it. I don't know if you understand the question, but I'll tell you what I mean. We're going to find all the points where it's not continuous, and for each of those points, we're going to find the limit of the function as x approaches that point. Here's the function. I didn't tell you the function yet. X squared plus x minus 6 over x squared minus x minus 2. All right? So this is kind of a two-part question. First, find me where are the discontinuity points, and then tell me what these various limits are as you approach those points. So let's talk about where are the discontinuity points. To find the discontinuities, you set the denominator equal to 0 and solve for x, right? Sometimes you can just sort of guess what the what values make the denominator equal 0, but this is a quadratic. There's actually going to be two answers, which, in my opinion, I don't want to worry about guessing two answers and make sure that I get them all right. I set this up as this equals 0 and then solve for x. Anyone know how to solve that for x? Something like that? There's a few different ways, I suppose, although there's one way I prefer. Yeah?
You could add 2 to both sides.
I would suggest not adding 2 to both sides. This is the classic blunder. Because the problem is there's an x squared and also an x. There's special things you got to do when it's like a quadratic. Yeah.
Make it x squared minus 2x plus x minus 2, and then split it.
Yes, I didn't follow what he said. I think you were saying the correct thing. You do one of these things, right? This is you want to factor this. When you have a quadratic here, you either want to factor it, or if you're crazy, you can use the quadratic formula. I'm not into the quadratic formula, but you can use the quadratic formula if you want. I apologize if your mom invented the quadratic formula or something. It's not crazy. It's very useful, but I would prefer to factor every time. I'm going to prefer factoring. What do you get for the factors here?
X minus 2, x plus 1.
X minus 2 and x plus 1. Yes, I agree. I hope you remember how to factor. I said before, this is super important in this class. All right, continue. I'm trying to solve for x here. So this means x minus 2 equals 0 or x plus 1 equals 0. Solving for x each time. X is 2 or x is minus 1. So those are my discontinuity points. There are 2 of them, and they are 2 and negative 1. All right? That was the first part of the question. Find any points of discontinuity. And then, for each one, find the limit as x approaches it. So what I'm going to do here is find 2 limits. I want to find, first of all, lim x approaches 2 of this function. X squared plus x minus 6 over x squared minus x minus 2. Right? And then, so that, I'm going to work that out. Leave some space. I also want to find the other one, too. Lim x goes to minus 1 of the same business. All right? And this is the second part of this question that I'm asking you to do. Each of these limits you want to do using the methods that we talked about, last time, or the way you did it on the homework. Try to plug the value in, see what happens. You might have to go back and simplify and cancel. So I'm going to, the first one, begin by plugging in 2. I get 2 squared plus 2 minus 6 over 2 squared minus 2 minus 2. This is 4 plus 2 minus 6 over 4 minus 2 minus 2. That is 0 over 0. Unfortunately, that means you have to go back and simplify with the hopes of canceling something or other and then plugging in again. So I go lim x goes to 2. I'm going to have to factor on the top and the bottom in order to simplify. Now the bottom, we already know the factors of the bottom. This is what we did before. It's x minus 2, x plus 1. Can anyone say what are the factors on the top? Yeah.
X plus 3 and x minus 2.
Plus 3 and minus 2. I agree. Great. All right. Can we simplify? Yes, we can. Cancel x minus 2 and x minus 2, right? So what remains is lim x goes to 2, x plus 3 over x plus 1. Plugging in, x equals 2. I get 2 plus 3, 2 plus 1. That's 5 over 3, and that's the answer. 5/3. I hope that's what you got. Any questions about that one? All right, and then let's just do the other limit by the same methods. Here I will start by plugging in, see what happens. I go minus 1 squared plus minus 1 minus 6 over minus 1 squared minus minus 1 minus 2. This is, I hope you get all your minuses right. 1 minus 1 minus 6 over 1 plus 1 minus 2. That is 0 on the bottom and negative 6 on the top. What does this mean? This means the limit does not exist. So for the first one, there actually is a value of 5/3. For the second one, the limit does not exist. All right. Can we just say what does this all mean? Like, what do these limits actually mean about anything? It means this graph, whatever it is, what it looks like, this limit, as it approaches -1, the limit of the curve does not exist. That means that the curve values don't actually go to any particular y value. That indicates that this really was an asymptote. So at x equals -1, this has an asymptote. That should be your interpretation of this curve. And near here, the thing does something like that. Or maybe it's the other way around. I think it's like that, though. All right. And then the fact that this one is actually a number, this one actually equals 5/3, what that means is that there is a discontinuity point at x equal 2. So here. But there is also a limit of the curve. So the curve actually does go to 5/3. It's just that there isn't a point there. So what that means is the curve here looks like one of these. It has an empty circle with no filled in part. And then that point right there, the y value is 5/3. So these limits, they tell us something about what does the graph look like near this point versus this point. The answer is near 2, it looks like a hole in the graph. Near -1, it looks like an asymptote. So they're quite different looking. Yep.
For the first part where you said the denominator equals
Yes.
0, if like on the test or the homework we can look at that and just know what
You
the
can
two
guess
numbers
the-
are?
Yeah.
Could
That's
we-
all right.
Could we like skip showing the works?
Yeah, that's all right. Yeah. Yeah, in general, if you can do certain steps in your head without writing them, then that's okay with me. If you don't write anything on the test and you just write the answer, I will become suspicious and think that you're copying from the person next to you, especially if they write a ridiculous answer and you copy a similarly ridiculous answer. Something ain't right, I will say. But yeah, I mean, I think we all know when it's reasonable that you could do something in your head, and by all means, do it in your head if you want to. All right, I got one similar to that one for you all to try, and I think that might do it for us. So, same question. I will write this formula first. X squared minus 2x minus 8 over x squared minus 3x minus 4. All right, your job, I'll write it again. find all discontinuities. And find each limit as x approaches them. I'll try and put the previous one on the screen a little bit so you can still see it. All right, I'm gonna walk around again and see how you're doing. Feel free to talk to your friends if you like.
Oh, yeah. You get like X minus 4 and 1 plus I mean, negative 4 and 1. That's your, like, yeah, I remember that.
This is the last one.
Yeah, I think we'll
Actually,
Pretty good? Yes.
So it's not negative 4 and 1.
Negative 4 does.
It is.
Plug in negative
It's like
negative
negative
4 squared.
Except for 0. So do we always put it towards the other side? We gotta do both of them. I mean, we can you do both. Yeah. Oh, right.
So for the, this is factor, right? Oh, it's factor.
But let's say that factor differently and then
Oh,
x was
so we're-
minus 1 and x plus 4, would that matter?
And that's what, that's the discontinuities?
It would.
Yeah.
And then the limits
This is
is what was.
Then just set,
Plus 1, which adds up to negative 3x.
Yeah.
set like this to 4, set x to 4.
Oh,
Like the answers you get here at the factor, those have to be able to plug in the denominator.
That's right.
So you can like test to make sure.
Yeah, I mean, that's how you found these arguments.
Yeah.
Did you buy the textbook yet?
Do you have out the questions. Yeah, is he gonna make sure of it? Thank you.
This is just text me and I'll send it.
So you want to find the discontinuities?
There should be another limit. How many classes are there? I had 3. You carved it from where?
All right, can we chat about these? I see a lot of people finished, some people not quite done, but that's all right. In general, I'm not big on making you do these really quick. So find all the discontinuities and find each limit as it approaches them. We need to start by finding what makes the denominator 0. So you should set this up. Set the denominator equal to 0. This you got to factor, and I saw most people factored properly, like so. And then you, having factored this, you can solve for x. So I go x minus 4 is 0, or x plus 1 is 0. This means x equals 4. This means x equals negative 1. So these are my two discontinuity points. An easier question, I might just ask you, what are the discontinuity points, and leave it at that. This would be your answer if that were the question. I also said, so find all the discontinuities. Oops, that was what I just did. Next, find each limit as x approaches them. So I need to do two limits now. One will be the limit as x approaches 4, and the other will be the limit as x approaches negative 1. Hopefully I can do this without messing it up. I go lim x approaches 4 of that same function, x squared minus 2x minus 8 over x squared minus 3x minus 4, right? I think I got that right. You should begin by trying to plug the value in and see what happens. I plug it in, I get 4 squared minus 2 times 4 minus 8 over 4 squared minus 3 times 4 minus 4. This is 16 minus 8 minus 8, which is 0. This is 16 minus 12 minus 4, which is also 0. So that's 0 over 0, which means we need to simplify and cancel. Here, the simplifying is by factoring. The bottom, I also already know how to factor. What'd you get when you factor the top? Somebody. Minus 4 and plus 2. Somebody said. I think that's right. Now I can cancel x minus 4s, and I end up with 2x plus 2. Come on now. X plus 2 over x plus 1. So this is 4 plus 2 over 4 plus 1, which is 6/5, and that's the answer for this limit. I hope you got 6 over 5. Any thoughts about that one? All right, and then the very last bit here, x goes to minus 1 of the same function. X squared minus 2x minus 8 over x squared minus 3x minus 4. This I'm going to plug in again. I get minus 1 squared minus 2 times negative 1 minus 8 over minus 1 squared minus 3 times negative 1 minus 4. This is plus 1 plus 2 minus 8 over plus 1 plus 3 minus 4. That's negative 5 over 0. The limit does not exist. I hope you got something like that. And I think since you're going to be watching the videos anyway, rather than starting the next bit, maybe we'll just leave it at that. So I hope you all have a good week and a half. Please let me know if you have, I have time right now. If you want to chat about homework problems, I'd be happy to look at them with you if you want. Otherwise, see you next week.